Welcome everyone. Yeah, thank you for coming. And today we have Dr. Chandrakant Singh, who is a postdoctoral researcher at Chalmers University of Technology. And it's one of the foremost university in Sweden. Yeah, and he has done his PhD in sustainability, isn't it? And I think that was from Stockholm University in Sweden. Yeah, okay. And currently he's looking at deforestation carbon footprint of global food production and consumption. So it's a pleasure to have you here. You have traveled a long distance, I guess. Please introduce us to the topic, and there will be questions at the end. We are happy to have you. Thank you.
Good afternoon, everyone. It's a pleasure to be here. Thank you, Dr. Vishwama, for introducing me and giving this opportunity to present my research here. My name is Chandrakant Singh. As said, I'm a postdoctoral researcher at Chalmers University of Technology. Previously, I have done my PhD in sustainability sciences. From most of the research that I'm going to present now is from there. Also from TU Delft and IASA. Let's get into the presentation and we can discuss more. So my presentation has three main sections. Background about tipping, introducing it to the concept of tipping points, and briefly introducing what these global tipping point elements are, and briefly also about what previous tipping studies have done, what kind of knowledge they have provided, and where the gaps currently lie. And then we are going to discuss some of my research on assessing tipping risk using remote sensing and process-based models, which basically is divided into three parts, like how forest responds to changes in water availability, how what's the forest resilience with changing hydroclimate, and what parts of the forest are at risk of tipping under future climate change. And this is just for fun. I'm going to talk a bit about my interest with the topic and forthcoming research. Very briefly, I'm not going to bore you for long. And then some key takeaways. Before we get into the topic, I want to ask how many of you have heard the term tipping point? Kind of know what it means. Okay, we have a good number of people. You might have heard the term Amazon is near critical tipping points. You might have heard that Greenland ice sheets are tipping, Antarctic ice sheets are tipping. Before I tell you what this tipping point is, I want you to answer another question of mine, which is what makes an ecosystem prevail under its current environmental conditions? Why is Sahara Desert in the place where it is? Why Amazon rainforest or Congo rainforest is in the place where it is? What is the factor that governs this? Yeah. Yeah, okay. ITCZ. Anyone wants to take another guess at what that would be? Any guess is fine. Okay. Yep. It's a combination of these factors. It's what's called historical conditions or legacies, which is which includes climate condition, biotic, abiotic interactions, disturbance regime. It includes how human interacted with the ecosystem. And ecosystem, what it wants to do, it wants to be in equilibrium with the climate that it is currently experiencing. And this interdependence between climate and the ecosystem gives birth to a set of feedback. And the benefits that we enjoy, which is regulation of water cycle, for example, is an ecosystem service of those feedbacks. But over last few decades, humans have modified the climate conditions to which ecosystems were adapted to. And ecosystem again tries to be in equilibrium with its environment. And this leads to generation of a new set of feedbacks that it tries to adapt to. And as an impact, we currently see global warming, drought, forest fire, and it also it also perpetrates in our social ecological system. We see current global food and water insecurity. As I said, tipping point basically means abrupt and potential irreversible shift in the state of an system. So let's take an example. Oh, sorry. Let's take an example. Let's say there's a system where there's a biotic component and an abiotic component. Biotic component could be tree structure. Abiotic component could be sunlight. When there is no feedback between these components, you often observe a linear response. When you change the condition of the system, there is also change in state. For example, sunlight influences photosynthesis, which leads trees to grow. But more trees growing doesn't mean that there's more sunlight in our system. When there is a weak feedback, still a feedback, you start to observe a bit of non-linearity, an abrupt shift. The system kind of remains stable for most part, and then you suddenly observe the point where then there is a sudden collapse in the current state of the system. When the feedbacks are too strong, for example, in our current natural system, then there is a discontinuous transition, which we call as tipping point, where you observe a similar abrupt transition, but it's called catastrophic. In a sense, it's irreversible. Can anyone tell me by looking at this figure why it would be irreversible or potentially irreversible? Yeah, but this one also had lots. Uh, yes. The official definition, let's take it on top again. Tipping point are thresholds beyond which there is significant reorganization in system structure. And these reorganizations are abrupt and difficult to reverse, even if the influence of the drivers are diminished. So you see that when there was a system, it existed at certain condition, but after a certain point, it skipped to a different system. Now the system has stabilized in its new condition, and now you need to cross a much higher threshold for the system to bounce back or tip to its initial condition. So it does not follow the same pathway to recovery. Uh, Discussing this tipping point is important, let's say in case of forest ecosystems, because a lot of forests regulate our climate, regulate what cycle. Permanent loss of forests could lead to some irreversible impacts, such as permanent loss of biodiversity, more carbon in the atmosphere, leading to more global warming, but also to livelihoods, such as human livelihoods, such as food insecurity, water insecurity, ecosystem services that we enjoy. Knowing this, where these tipping points are, would also allow us to develop early warning signals and work on the preventive measures. But not everything is just doom and gloom. Sometimes we also want to promote a system stability, a system resilience. So sometimes we also want to recover a degraded ecosystem back to a lush forest, say, for example. Ever since Buzz Holling's 1974 paper that these complex ecosystems have multiple stable states. There have been a lot of research on tipping points, but the empirical evidence is that where these tipping points are, in fact, if ecosystems have multiple stable states, have been lacking. It was not until late or mid 1990s that some evidences start to emerge in our natural ecosystem. You might have heard of turbid and clear lake. That if you would only find lake that if either clear or turbid, you would not find like semi-murky shallow lake. And as you load more nutrients in a clear lake, there would be a threshold beyond which that same lake would turn turbid. Same with coral shifts due to climate warming. There were some other empirical evidences of habitat shifts. You could see there is a sudden shift after certain overfishing. There was a really great paper from some of the colleagues from Stockholm Resilience Center, which looked at some of these global tipping elements. These are some of the tipping elements that are imperative to the stability of Earth system, but they have a likelihood of tipping under current or near-term climate change scenarios. You could see Amazon rainforest is one of them. You could also see Greenland ice sheet loss, Antarctic ice sheet loss. You have permafrost collapse. You have Atlantic Ocean circulation collapse, and so on. Getting now focusing on just the forest part, evidence to whether tropical forests have these alternative stable states came in. There were theoretical studies there, local studies there since 2000, but biome scale study was published in 2011 by Hirota et al. She was from Martin Shepherd Group in Wageningen University of Research. She found that tropical terrestrial ecosystem exist either as forest or as savanna. When I say forest, I'm talking about really densely packed green lush trees, more than like 70%, 80% dense. On the other hand, savanna is this sparsely growing trees, remote sensing data sets were coming up, and this one was a tree cover data set from MODIS, which basically mapped at a 250 meter pixel range how dense woody vegetation is within a pixel. And you can already see for Amazon that either trees are really dense at maybe more than 75, 80%, or they are sparse. You would rarely find some ecosystems that lie in the middle. When you compare these pixels with precipitation for that pixel, you would find that there were some clusters that were forming. You would find there was a cluster where even though precipitation decreased from nearly 3,000 to 1,000, the structure of forest did not change. Same with savanna, that you increased its rainfall from 0 to 2,000. The structure was still very sparse. And then after that, you would not find any forest. After this, you would not find any. After this, you would not find any savanna. After this, you would not find. So they concluded that there are some stabilizing feedbacks that are trying to keep the forest in a stable state, even though the condition has changed through some adaptive mechanisms. Same for savanna as well. And they did not discuss too much what these feedbacks are, generally that they are. And after reaching this tipping threshold, there would be an amplifying feedback that would push forest or savanna outside of its native stable state into the alternative stable state, looking something like this. And following from 2011 to 2022, there were a lot of studies that tried to look at, okay, what these reasons could be, what the reason for that could be. There were papers on that, okay, this stability could be due to human influences. Yes. There was one on fire, that fire is the key factor that might push the ecosystem, which are very dry, to savanna, and then would stabilize them as savanna. Herbivory pressure, that there might be too much cattle ranching, could push a dense forest into a savanna state, and so on. Following this precipitation logic based on the thresholds that we saw, paper by Ari Stahl in Nature Communications 2020, they tried to look at how forest ecosystems would look like if we try to project the thresholds that we found out, how ecosystem would look like in the future. So they did a very interesting experiment. What they did is they assumed that the whole continent, that tropical continent, is either forested or deforested. So they did two experiments. They assumed that whole continent is forested, and you force the current climate rainfall on them, and you see how much forests are left when the whole continent is forested. And you do the same when you assume that the whole continent is deforested. You force the current climate rainfall, let's say there is a tree growing here and 1,000 of rainfall is falling on that. You assume that it's forested. When you deforest it, you still assume that 1,000 of rainfall is falling on it, and you see that if that forest would grow back. The regions that you see in beige or like the orangish color are for the forested experiment. So when the whole continent is forested, you would lose Amazon here, here. You would lose some parts of Congo here. But when you deforest the whole continent and you still have the same current climate condition, only the green part would grow back. So you see that already a major part of Amazon is already lost. They did the same experiment for the late 21st century climate under RCP 8.5. And they found out that some parts of the continent, the one that you see in red, would never grow back. This is the called Guiana Shield. It has French Guiana, Guiana, Suriname, and those countries. On the other hand, Congo rainforest gained some forest in the future climate. Southeast Asian forest does not change much. And this aligns with precipitation changes on the future RCP 8.5, that you see some dryness here, you see some increase in rainfall here. So it made sense. Okay, so Amazon might not recover under future climate change. So that was their conclusion. But I had a problem with this, or just the precipitation metric. Based on your knowledge, which climate do you think is more likely to hold the forest? They both have they both have the same rainfall all year round. I'm assuming most of you would say this one. Precipitation in itself, while it provides you estimate of total water availability, does not tell you when forest is getting that water. Does forest require that water when it's getting it? So we came up with a metric to substitute precipitation. It's called root zone storage capacity. We wanted a metric that would represent how much water vegetation would need, or at least to store for it to survive during dry periods. The concept is called root zone storage capacity. It's based on mass balance metric. Root zone is the region besides root from which vegetation absorbs its water and nutrients. Everything falling outside of root zone would leach out of the system either through runoff or would go into deeper soil layers as groundwater and those storages. It's based on simple mass balance. We basically looked at daily time step, how much deficit occurs at individual time steps, how much surplus occurs at individual time steps. Based on that, we get daily water deficit. We sum it up to look at what's the maximum accumulated water deficit a forest is going to experience. Not the maximum, but maximum accumulated. And because that is the maximum amount of deficit a forest is going to experience in its time period. And that is what it needs to adapt to for it to survive. That was the basic idea with this metric. We based this based on evaporation precipitation, and we made sure that our precipitation and evaporation metrics were free from any vegetation related adjustments or soil related adjustments, because we are talking about root zone in the soil. So now you see you have, again, the same data set with high tree cover, low tree cover. On the other hand, when you look at root zone storage capacity, you find that it's quite less in the central part of the Amazon, keeps on increasing to somewhere on the edge of deforestation region of deforestation, and then in the savanna, it's again less. So we drew straight transects from densest part of the forest to savanna in every possible direction. We tried many more transects. I think these were representative of what we found out. So basically, it looks something like this. So this is transect 1. You need to focus on some lines. So this is tree cover density. So very high tree cover density, 80% goes down as you go towards savanna. This is root zone storage capacity, the one in blue. It's initially less, it increases to a certain point and then decreases. There are two smaller lines here. One, the dashed one is groundwater table depth, and the another one is rooting depth. So what we found out was in the densest part of the forest, because part of the forest receives ample rainfall throughout the year, evaporation never or rarely exceeds precipitation. That forest already has enough water for itself. It does not need to invest in its root zone. We find root zone storage capacity, but then you also see that the rooting depth is very shallow. So the densest part of the Amazon did not have very deep roots. It had very shallow roots, but like really, it's called buttress roots. So it helps with the stability of really large trees, but they are not deep. As you move along the transect, you find that the tree cover remains the same, but now you see there is a slight increase in root zone storage capacity, which we classify moderately water stressed. For these ecosystems, we find that there is a bit of seasonality where evaporation in some seasons exceeds precipitation, and the forest needs to adapt for that water deficit it's experiencing. As you move further along the transect, you would also see some increase in rooting depth here. But then when you move to this point where you have really maximized root zone storage capacity, we find that forest kind of showed some specific behavior. So there were very significant seasonality that in some seasons evaporation would be super high, but then there would be no precipitation. But rooting depth kind of maximized at certain point. Forest cannot indefinitely expand like 100 meters down without having some consequences on a structure. What we found was that maximizing rooting depth kind of created some risk of hydraulic failure. So when you have really expanded your roots in the soil and you do not have water, you sometimes kind of uptake these small bubbles, and that kind of disrupts the flow of moisture from soil to the leaves, and that leads to these trees dying. Some of these trees also kind of shedded a lot of leaves, which is good that they reduce their evaporative demand, but shedding more leaves means that you have more dry leaves, means that you have more fuel for fire. And then when you have more fuel for fire, then you have more fire-related mortality. And that kind of opens up the ecosystem, and now you suddenly transition to something like this, like landscape from Lion King, where you have ecosystem with really low water availability and demand. Root zone storage capacity is quite less, nearly about, can go as low as 100 mm. Interestingly, we find that these species also had really deeper roots going as far as 20 meters. But we also found that most of their root biomass was concentrated in their shallow depth. It means it was a drought coping strategy, very strategic, because these ecosystems have to compete with grass species, which also have most of their biomass on shallow layers. So as soon as moisture becomes available, they quickly want to store it for dry periods. So this was to increase their competition with grass species, because grasses can just go dormant when there is really dry climate and then can grow back up. But trees do not have that capacity. So, okay, so using root zone storage capacity, we tried to look at how vegetation structure changes. Our goal in the end was to use root zone storage capacity to project tipping risk. We had to do an intermediate paper for that, which was to prove, okay, we say root zone storage capacity is more representative of the transient state of the system, but does it actually represent what we say? So we did a resilience-based metric. This was the same that Hirota used for their resilience calculation. We did the same, but with root zone storage capacity. And we found that some regions in this arc of deforestation were less resilient than what previous studies have showed them to be. On the other hand, ecosystems in the deeper parts of the forest were more resilient than previous studies showed them to be. And Congo was more resilient altogether. Uh, and we said that do not believe our word for it. We compared our resilience metric to tree cover change. So our idea was if forest is more resilient, it would buffer these hydroclimatic variability and would remain same. But if forest is less resilient, it would show more changes to its present tree cover structure. And we got a bit more correlation than just precipitation. Okay, so we cleared most of the hurdle. We went into the next step of projecting tipping risk using uh, this rules on storage capacity. And this paper really took considerable time for us to get it published. Uh, so we had this, if you remember, we had this figure in paper one. So what we did is to build upon previous study of Aristotle, we said, okay, besides projecting tipping, we're also going to provide a classification of which forest is also more vulnerable to maybe further warming and even after future climate change. So we assume that if root zone storage capacity of a forest increases, we would say that it's becoming more water limited. If it reduces, we say it's less water limited. And if it crosses a certain threshold, we say, okay, it has tipped to a new state. We did this study across 4 scenarios using nearly all the CMF6 data we had, nearly of 33 models at that time. And we found that nearly 1/3 of forest area is influenced by climate change. Interestingly, we found, as previous studies also did, that this guana shield part was most vulnerable, but we find that if we stick to the least severe climate scenario, SSP 1, 2.6, our tipping risk would also be significantly minimized. Whereas under SSP 5, 8.5, it would be very significant. But regardless of this, there would be a lot of forests that would go into being more water stressed, regardless of which scenario you choose. Congo still showed some lot of resilience, that its currently water stressed forest did not increase from its current condition. And in Amazon, we find that this risk grows nearly 1.7 to 5.8 times as we increase the warming from SP1 to SP5. So we found what previous studies find, we added a bit more to that. But then it was also the case, like, why is that happening? Why that guana shield part is so vulnerable? Why the southern part of Congo rainforest is so vulnerable? So there is some tipping risk in the southern part of Congo rainforest. So we found that primary reason is this intertropical convergence zone. Under future climate change, it's predicted that there would be a southward movement of this ITCZ, which is this really high, what do you say? There is a lot of solar radiation on that ocean point, which leads to a lot of evaporation from that, and that moisture moves along, and it kind of sucks in the trade winds from neighboring regions, and it precipitates on these regions. So when there is when the sea surface temperature warms up in the future, this ITCZ would shift southward, and this would kind of, the moisture that was moving from Atlantic Ocean, from this guana shield, all the way exits from La Palta Basin, would move southward, and it would just completely miss this whole guana shield. On the other hand, for Indian Ocean, it would move northward. So the forest that was here kind of risk tipping because there is no more moisture there. But there's also other things that lead to this, which is that not Amazon rainforest and Congo rainforest are not the same. Congo rainforest seem to have evolved under several episodic changes to water availability, which makes it more resilient under current environmental and future environmental conditions compared to Amazon, which had been very moist even in its previous climate. Uh, and this was also corroborated by a study by Hubao et al., which found that in recent years, there is a saturation in carbon sinks of Amazon rainforest, where you see it's decreasing with growing climate change, whereas African Congo rainforest is more or less very stable. And they had found out that while Amazon rainforests are dynamic in a sense that when more CO2 becomes available in the atmosphere, they try to sequester it quite quickly. They do not invest a significant portion of it in its drought coping strategies compared to Congo, which makes them really sensitive to uh, this climate-induced pathway, climate change pathway. Okay, so this was the study about tipping risk. Now I'm going to talk about a bit about how we are moving forward. So one thing that you probably all saw missing was we only talked about uh, natural degradation, climate-induced changes, climate-induced forest loss, but we did not talk about human influence forest loss, deforestation. This is a study that is currently in preparation. Basically, what it does, it looks at how human influence over land system can influence downwind land systems. Basically, it tracks moisture, from where it evaporates, where it ultimately precipitates, how much moisture loss can we assume would happen when you remove the forest from that specific land system. Interestingly, we found that these are some preliminary results. We found that the smallholders, which are landholders having less than maybe 100 hectares of land, uh, because they are situated very close to forests, they are they critically influence forests quite much. On the other hand, large landholders influence agricultural lands much more. However, uh, forest resilience, which is how vulnerable are forests towards changes in hydroclimate. We found that under large landholders, water influence or moisture influence, because they are settled in forests that are quite less resilient, they might likely influence more tipping still than smallholders. Uh, this is one of the study that got accepted a few days ago in Nature Foods, where we looked at. So I wanted to go much more finer in terms of, because presently we only looked at broader land use, but I also wanted to know if soy is grown on a deforested land, how much that influences precipitation somewhere else. If oil palm is grown somewhere on Indonesia on deforested land, how much that would influence downwind land systems. But when I tried to do that, I found that there is a major gap. There does not exist a data that does this commodity level deforestation attribution. So for our first step, we did this deforestation attribution at commodity level, covering nearly 180 countries and commodities. You can find more on deforestationfootprint.earth. But this is important because more than 80% of total deforestation is driven by agriculture. So it's a very significant number. And of this total deforestation, nearly 30% is internationally consumed. It's not even domestically consumed. So it's, for example, China is a major importer of soy. A lot of countries are major importer of oil palm, and so on and so. This study is also in preparation. You might see sometime soon as a preprint, where we also added another dimension to that, which is finance, which is how much countries influence global supply chains. And we find that for Amazon, this deforestation is significantly tied to indirect influences. So the companies would fund, maybe let's say some company in Switzerland, which would have a subsidiary in Amazon, and then that would influence deforestation indirectly. The idea with this is to connect how deforestation-induced water risk kind of penetrates in our global supply chains and financial networks and influences sustainability. Okay, now one just last slide. So if I have to consolidate what I talked about as key takeaways, so one would be our understanding of how vegetation responds to climate is quite limited, and there needs to be more empirical data for us to know the behavior of the ecosystem, and especially subsoil moisture dynamics are specifically lacking in our current empirical evidences. Most of the tipping is avoidable if we try to steer towards a less severe climate change scenario. And this one, I think everyone at this center would closely relate to, because it's an interdisciplinary center that uh, biophysical, uh, biophysical land atmosphere interaction, land climate interaction have developed mostly in isolation compared to food production and sustainability research. And there is a significant need to integrate these disciplines if we want to have a better integration of both science and policy. And with that, I end this presentation and open the floor for discussion.
So the first question is when you were talking about terrestrial ecosystems and the bistability of them, right? Tropical terrestrial ecosystems. You said it's either a rainforest or a savanna, but Sahara also exists in the same latitude. So that's another possible desert is another possible.
Yeah. So the definition by Hirota was quite loose, in a sense that what they did not classify it based on biome, they classified it based on density. So forest is anything that where woody vegetation is packed more than 75%, like really close trees. Whereas savanna was, it could be sparse vegetation, and sparse vegetation also included our like savanna-like state, which included barren land as well. So barren land is also a tipping point. There could be a case where, let's say, climate has transitioned so much severely that there was no rainfall after a certain point. At that point, you would not even find cactus species growing on that land. So barren land is also included in the classification savanna. So savanna and savanna-like state.
Okay. The other question is that when you're considering RCPs, that's mostly about climate forcings, but it doesn't directly take into account any deforestation activities by us, right? Uh,
Yes.
and I think you were trying to say that that's going to be the next major direction of your work, but I was thinking that probably the bigger threat to large rainforests, like especially like Amazon, is deforestation by humans rather than climate directly.
It's divided at 50%. There was a paper in Science, like in 2016, which says degradation is even more threatening, but it's deforestation-induced degradation as well, like near term. In our paper, we acknowledged it because we are using forcings from a already developed climate model. We cannot take out the factor of human influence, and it would be very difficult to predict where deforestation is going to happen by end of 21st century. So we did an analysis to suggest that what we project using just climate forcing does not overlap with what CMIP 6 land. So CMIP 6 does not how do you say, dynamically tells you land use change. It's kind of, it's also forced. You know your land use before you even run your model. So we found that there are some discrepancies to that, and there needs to be better, as I said, better empirical evidences, better evidences on where these human disturbances are going to be, but also climate, how climate in the future would interact with society, how society based on the future climate, how they would influence land use. So this is currently lacking in our study. And we try to very broadly acknowledge that this is a major gap, and there needs to be a coupled human biophysical interaction for us to actually tell where the actual tipping is going to be happening. By the way, thank you for this question. If I want to add one more point, so maybe some of you might also be thinking, why can we project tipping? Like we have climate models, can we predict tipping. So we cannot. The tipping point is also called something as emergent property of the system. So even if you have details about the system, you cannot say when the tipping and where the tipping is going to happen. So it's done mostly based on these empirical studies. So even if you run a CMIP6 model for, let's say, 2300, you would still not see that the forest has tipped. It would say that it's low for vegetation. It would not say that this is due to tipping.
Just one final question, which is not, I guess, not too related to your work. The climate scenarios that were calculated, the different RCP scenarios, that was still calculated with some ideas about business as usual, some amount of cut down and that. But then right now we are seeing quite a bit more chaotic response from the world than the scenarios that were calculated. On one hand, we have China focusing on electric uh, renewable energy sources. On the other hand, we have US doubling down on the oil pathway, right? A few days ago, it kidnapped the Venezuelan president. So do you think we can stick to the older scenarios that were around for us when we calculated all of these projections, or should we now transition into newer, more drastic scenarios?
I think what was agreed upon was a temperature change, that we would not cross 1.52 degrees Celsius in the Paris Agreement. RCPs and SSPs are basically just telling that this much radiation is now in the Earth system, and that would increase the temperature of the Earth by this much. Of course, like still there are people who would say, okay, we can still go to less severe climate change, but then there are also that say that SSP1 scenario, which is 1.6, 1.7 degrees, now completely impossible. We are already on trajectory to SSP2, 4.5. I think it's a very difficult question to answer that, whether it's a voluntary number, right? Based on well-educated scientists at that point. I think what's important is that there needs to be stringent policy actions that would, rather than saying that, okay, it's a voluntary number, like you need to be below 2 degrees or 1.5 degrees. If you are above it, we are fine with it. I think there needs to be very stringent policy action that, okay, these are the things that can be done. There should be public-private engagement, how public authorities, private authorities can work together, how they can work with local landholders who are actually working on the field, who have these land systems, which are mostly responsible for the carbon emissions and so on. So that's what I think. If this number is realistic under current climate, that is a very philosophical discussion, and like can go on for several days. We might agree and disagree at some point, but yeah, that's what I think. Hmm?
One of them is that the Amazon is given by large topography, ocean. You have disregarded completely. What do you think in terms of scenarios? How is the ocean going to respond to in terms of the food capacity? How is it going to realize? Because I have not seen that, and it's a bigger factor.
Yes. So when we first used root zone storage capacity metric, someone also said that how soil comes into picture.
No, I mean that combo topography and some topography they are not.
Yeah.
They are different.
Yeah.
Now in terms of the ocean rate, they will be largely different.
Agree.
How you make such kind of map and you try to talk about the two bases if I try to see that one of them really have some glaciers in the picture, another of them does not have anything of that kind of high magnitude. How does that affect in terms of sustaining your forest ecosystem?
Yeah. The tipping thresholds that I talked about are not exclusive, that they are going to hold true across time.
So the system approach which you are doing, are you talking to soil system or not?
I'm assuming that when there is a certain evaporation, the influence of soil is represented in evaporation. So that was our whole point with using a metric that was not driven by soil or vegetation. That let's say if it's a a clay soil holds more water, but it does not percolate to a deeper depth compared to a sandy soil. But that evaporation from that ecosystem would represent the capacity of the ecosystem to hold moisture. So if there is a different soil, there is more erosion, it kind of washes away some trees. I'm assuming that would also lead to some reduction in evaporation as well, and that would represent uh, how how the ecosystem, what the current ecosystem state is. But I think these, what you said is quite important in terms of if you want to look at very micro scale, local scale tipping influences, because that specific region is what's being influenced by erosion, right? So at local scale, this exclusive 1000 precipitation threshold of tipping might not hold true. There might be several local factors that would influence it, which includes fire, which includes kettle pressure, which includes soil condition, which includes a recovery rate of that ecosystem based on current ecosystem conditions. It's a very difficult question now that I think about it, because I'm thinking of this erosion storage capacity from the climate perspective, and then you talk about what if you change things on ground. Yeah, definitely it's going to change how ecosystem responds, and might not follow the same logic. Okay, so our erosion storage metric takes into account annual evaporation and precipitation rate. So with CMIP6, because there was no annual precipitation, we did we used monthly data, and we tried to equate it with adjust it for daily deficits. But why do we need to distribute? Okay, so even you mean like over the day? Yeah, assume. Yeah, exactly. Yeah. I think that would increase erosion storage capacity, because when we shifted from daily to monthly, we saw that there was a slight dip of 100 to 200 when we used monthly. And at daily time step, I think your cumulative water deficit would also increase depending on at what time of day that ecosystem is experiencing their precipitation. Yeah, definitely. Yeah, that definitely would change erosion storage capacity if you look at this hourly, even this minute rate. Yeah. Hmm? Hmm? Ah, hmm. Yeah. Mm. Yeah, definitely. I would love to hear more.
Talking about my work, like we're working on past times, sometime 14 million years ago, and we are getting traces of a rainforest in deciduous to evergreen forest in Gujarat, which is a desert site.
Hmm?
So at that point of time, the CO2 was high around 400 ppm. We're trying to see how is that.
Yeah.
Kutch, which is a desert today, at around 420 ppm, was a very rich, very dense forest at roughly the same CO2 ppm from 14 million years. We're trying to see if the monsoonal system, which India has, was there or not.
Yeah. Very interesting. I've seen similar discussion with Sahara as well. That at some point Sahara was also green because there was a lot of rainfall. Right? Yeah, I've seen some papers on that, but I would love to see some of your studies.
I have a the graph that you showed with the root zone moisture and the density of trees. So you said when the trees are less dense,
Oh,
so yeah. So when the trees are less dense, the root zone storage capacity has increased. So it's just a curiosity question: is this the same type or
uh,
is it different species?
yeah. Can I? Yeah, just a second. Just before you do that, can I remove this? So I had made a modification to that figure, so I do not bombard. Yeah, just now it would come. So now you see this. This is an ecoregion. What ecoregion specific scale? So same tree species. It's not same in the ecoregion. It's some are very moist tree species. Some are on the fringe of this moist and dry species. Here you have more dry. Here you have coexisting dry and savanna species. I did not show it earlier because too much color might confuse you, but we did this analysis as well. And species are different. We tried to look at how individual species, if they have a tipping rate different from the whole ecosystem, because it might be that the velocity of climate change is too fast for moist species to acclimate to that, and they might completely die out, making dense part of the forest less resilient, right? But that analysis we could not do. We lagged really field scale data for that, but it was in works at some point. To spend some time on it. I might have some preliminary data for that. Yeah, so I said that Congo is more resilient to future climate changes because it has experienced these episodic changes in water availability and fire over previous time scales compared to Amazon. So it can survive in a bit more dry, fire heavy kind of environment, whereas Amazon has been very moist all in previous years. So as soon as now there is more warming, more drought, it's kind of it's not as resilient, or it might tip much faster than Congo rainforest. Yeah, yeah, exactly. So it's ecological memory. Uh, so yeah, yeah, yeah. And we also in our first found a very interesting thing that there was a grass species that was growing on these highly water stressed forests, which was C4 species compared to C3 in Amazon. And C4 species tend to be a bit more water use efficient. It means that they leave more moisture for uptake for Congo species compared to there is a significant or considerable competition in Amazon rainforest for water uptake. So that also probably this. So there is a mixture of ecological memory, disturbance regimes, but also the current species that are in the ecosystem. Mm. Uh, so the model that we are using is a Lagrangian model called Utrecht, developed by researchers at Utrecht University. And the resolution is 0.5 degree, but you can also ask them for 0.25 degree resolution. And it's based on ERA 5, which is also at 0.25 degree resolution. So evaporation is input to that model, and then it would distribute evaporation to downwind land systems, the fraction of evaporation. I do not trust any data, but it seems like it's good enough. Like my advisor is also has a different model, which also uses ERA 5, but uses Euler's moisture tracking method. and the estimates are more or less same, but the evaporation data that we use in our analysis, like in the initial analysis, we used 3 evaporation data and we looked at the sensitivity of that, and you could see significant difference in root zone storage capacity. So evaporation seems to be a metric that is in itself is really uncertain. Or E minus P gives you daily deficit, yeah. So there is a cap because we are talking about root zone storage capacity. We never go below 0 because we are talking about storage. So we assume, so it's never negative. We assume that the excess moisture that the ecosystem has got kind of now contributes to deeper soil layers and flows under gravity and goes to runoff. So it leaves the system. It does not stay in root zone, so it can be utilized by vegetation. Yeah. So, so it's daily time step. So here you see that you have surplus, but I do not say that there is surplus. I say it's 0 root zone storage capacity because the moisture is not stored in root zone because ecosystem already has enough moisture. So whatever is left, it just flows out of the system and contributes to other flows. Hmm. Yeah. Yeah, the deficit increases a bit. So it's the evaporation. So it's daily. Okay, okay. Now I get your point. Okay, so there are some exclusions to this model as well. We excluded human influence systems because irrigation can also act as an input. Okay. Hmm. 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 Yeah, but we are not looking at water bodies in this case. Oh, so you mean? Yeah. Yeah, but well, for Amazon, you maybe it's the other way around. For Amazon, you might ignore, but for Congo, I don't think they have well-established irrigation system. It's mostly dependent on rainfall. But yeah, 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 exactly. Yeah, the limitation section of this paper is also very heavy. If you see it, we have, okay, we only talk about the hydrological storage, not the actual storage. We try to remove human influence, but if it's traveling between some pixels, then we cannot ignore it. So it's broadly we are assuming that at the resolution of 0.5, 0.25 degree, it broadly evens out. But if you go much finer, I think there are several local factors that would be very critical when you include when you calculate ozone storage capacity. Hmm? So for this one, we had 2001 to 2012 because that's when we found the evaporation data for. Yeah, exactly. Hmm? Uh, so, and you're talking about just the signal of tree cover, right? So, a clarification. So, this tree cover does not tell you how green the vegetation is. It tells you the woody vegetation, like how closely packed the woody part of the vegetation is. So, an ecosystem might be flourishing during wet season and might shed all its leaves during dry season would not influence because the biomass part would be same. But the data set that we use, so this is a tree cover from MODIS, but then you might have also heard of a data set called Hansen tree cover loss. It's a global forest loss data set. And even they were like, they had to aggregate 12 years to know where tree cover gain occurred because it's so uncertain compared to tree cover loss, which is easily detectable by remote sensing. So we need to talk about in really like decade scale time frame for us to talk about afforestation and similar conditions. Hmm? So this transect is based on, so if I had removed this transect, you would find that this transect kind of looks very different compared to, so we had transect at nearly maybe every 5 degrees, and we tried to analyze it like this. So we try, but so both are changing along this transect. Uh, First of all, but also uh, we looked at some specific metric, which was covariance and relation, based on which, and we found where we had these unique patterns between all the transects that we had. So if you look at, we had 6 transects. If you look at all those 6 transects, you would find that the trend is a bit different. You would find that after savanna, it might be stable. After savanna, we had sometimes included human influence land use to get a completer picture. So we try to include transects which are dissimilar. So our story is more coherent, that the trend hold true regardless of which area you choose. Yeah, but so let's say you choose a transect like this. So then you would find that, yeah, exactly. So the root zone storage capacity goes up, but then the story is still the same, right? This we did this from densest part of the forest to savanna, so the shallow, the less dense part of the ecosystem, to get a transition that would be analyzable. I can check, but I did not specifically look at that. Mm.
Water availability.
Mm.
So that is also
Yeah.
not only in terms of let's say water through plants and so on, but also the precipitation patterns.
Yeah.
Then it started to grow back. Levels of certain meters.
That there might be significant influence from local moisture recycling. That
Exactly. So
yeah.
how would that look in the data?
Um,
And I think that question is still relevant. That precipitation patterns are changing in terms of also their intensity in
Mm.
the future. So if I get it in a month,
Mm.
so that happens over 10 days over a month, not just in 2 days over a month.
Mm.
That is very specific for
Yeah. We did this analysis in the global change biology paper. So there was a very interesting ecosystem here, which fulfilled all the conditions for a forest ecosystem. But because the rain, like it's a flooded ecosystem, so rain fell in 3 months, like really heavy rain. But still, it's a savanna because it would uproot all the vegetation that has grown over the time period, and then, despite fulfilling all the conditions, on the other hand, we found that there was so this part of the region near the base of Andes, uh, there was very less rainfall, even like 500 to 700 which did not follow suit for a forest ecosystem, but forest ecosystem exists. And we found that the runoff from melting of Andes kind of contributed to, so there are these kind of abnormalities and inclusions from other flows as well.